All right, thanks everyone for coming to the talk today. My name is Eric Katzfey. I'm the Chief of Software at ModalAI. And the topic of the discussion today is how we got PX4 running on a Qualcomm QRB5165 system-on-chip device. Let's see this. All right, so the agenda basically, first of all, why would we even try something like this? Then a little bit kind of overview of the architecture, what's inside the device, and how are we going to put PX4 on that. Some of the challenges of the build environment. The fact that this is a Qualcomm device and it's based on a very large amount of Qualcomm code. Some of that is proprietary. It's not open source, so we can't share it. And so what we had to do to get around that and make it so that an open source flight stack can run on top of this proprietary software. Along the way, there's been an awful lot of challenges in actually making this all work. So I'll go through some of my favorites in a couple slides. And then kind of where we're at and where we're going with it. And finally, I'll open it up to some questions. Okay, so first of all, why would we even do this? Well, if you look at the Qualcomm devices, they're actually pretty compelling devices. They have an awful lot of horsepower. They have all kinds of different sorts of compute accelerators they have GPU, they have for running neural nets, they have DSPs, modems, obviously. This is a Qualcomm device, so they're known for digital communications. And then just a large 8-core, very powerful set of ARM cores for running Linux. So it's obviously a very small device, very powerful. It's meant for smartphones, so it's meant to run cool. It's and it's got a lot of power. So if obviously you're building a very small drone. You're very concerned with power, you're very concerned with weight and size. That's a great reason to try and integrate as much as possible on one device. Point 2 here, there was actually a comment after one of the keynotes about tighter integration between ROS and PX4. And that's one of the great things about putting this all together on one device is now PX4 and ROS and whatever other kinds of applications you're going to run on there, computer vision, machine learning, AI, that can all now be much more tightly coupled. You're not just going through a serial port and sending Mavlink messages back and forth. You can do more complete integrations and higher bandwidth. So that's a really nice reason. And third is kind of, I could probably spend the whole discussion just talking about history behind this. This has a history that goes way back to before ModalAI even existed. Qualcomm actually got PX4 running on a Qualcomm device many years ago. So if you're familiar with the source tree of PX4, you see things in there that have been there for a long time. So how hard could it be, right? It's already been done in the past on a Qualcomm device. We're just going to port it and make it run on a new one. No big deal. Just a quick little overview of the device itself and the board that we've built to host the chip. This is our Voxel 2 Mini, so very, very small. Don't have one in my hand, but it's very small board. It's basically, the centerpiece of it is obviously the Qualcomm device, so that takes up the most real estate. some connectors, but it's got integrated IMU. It's got integrated barometer, so some of the kind of standard things you need to fly a drone. It's got integrated onto the board in addition to a bunch of connectors so that you can connect all kinds of peripherals such as cameras and GPS and all the other kinds of things you need to connect to a flight controller. See some of the highlights here, 11 grams, so it's pretty lightweight, 42 by 42 millimeters, so very small. So this kind of goes back to the whole swap optimized. There you see 8 cores up to, 4 of them, one of them goes up to 3 gigahertz, so I mean there's an awful lot of processing power on this device, so pretty impressive. I think I'll save that for another slide, but yeah, many image sensors, expandability to do cellular, Wi-Fi, micro-hard, any of these different kinds of communications things, so pretty powerful device. Okay, this kind of goes back to the history part of it there. How hard could it be, right? It's like it's already been done before on another Qualcomm chip. We're just going to make it go on this new one. Shouldn't be a big deal. So this was probably a couple of years ago when we first started diving into this. This is kind of what we thought. I'll just say it wasn't easy at all. Still in process. It's been a lot of work. One of the really unique things, so if you look at PX4 architecture, I mean it's not X RTOS running on a microcontroller. This is quite a bit different environment than that. Not just hardware-wise, it's not a microcontroller, and not just RTOS-wise. So it's quite a bit different. This is kind of one of the main differences right here is that we've actually split PX4 across 2 different processors here. So the applications processor, that's what we call sort of the Linux, this 8-core, where we're running the Linux. That's the applications processor, and then I was mentioning that inside this system on chip device, there's a bunch of other DSPs and GPUs and things. One of them is referred to as the sensors DSP. Essentially, the DSP, this is a Qualcomm architecture. They call it the hexagon architecture. They designed this DSP architecture themselves. It's not based on any other company's IP. And originally, this was what was running their digital communications, the modem, but they've since added more cores in there to do things like audio processing, vision processing, and then this one that we utilize for PX4 is called the Sensors DSP, which is really handy because it's actually got a lot of I/O routed to it. So obviously, for a drone, you need external I/O, I2C, SPI, UART, these kinds of things. It's got it directly routed into this DSP. So it made a very handy home for running the PX4 sort of flight critical tasks. So if we look at kind of how we decided to split things up, the sensors DSP, that's where all the flight critical stuff happens. In fact, you can go and as it's flying, you can kill the applications processor. The sensors DSP is still running the flight stack. You can still fly the drone and control it. So all the critical flight stuff, real-time stuff goes on the sensor side, sensors DSP side, and then higher level things like the Mavlink interface, that's where the networking stack is, logging, you got access to the file system, data manager, these kinds of sort of higher level things that resides on applications processor. That's kind of the way we've split it up. But this kind of architecture gives you flexibility then. If you need an extra UART and it's not available on the DSP, but it is on the applications processor, Well, you can just put the driver, the module that you want on the applications processor, because it's all tied together through the UORB between the two. So it gives us some flexibility also in terms of I/O and where we decide to put drivers and modules. So if you have seen any of this in the source tree, you'll also see that there's actually, if you look in the platforms directory, there's not X, obviously. That's what most people are used to using. There's the POSIX platform, so that's typically like a Raspberry Pi or something like that. We make use of that platform for the applications processor side of it. And then the sensors DSP, you'll notice there's a platform in there called CURT. So that stands for Qualcomm real time. So that's their RTOS that they run on the DSP. So that is a whole new platform that's in the platforms directory in PX4. That's specifically for that DSP. Okay, so obviously you have to build all this software. It's a little bit different for this particular device. On the applications processor, that's kind of, if you look like in the POSIX platform, that's an ARM environment, and so there is ARM set up. But I think there's kind of a to-do item to kind of go back and probably look at that whole tool chain for 64-bit based ARM. Right now, since based on history, we've been using a Linaro compiler tool chain, and we've continued to use that, so it's a little bit different. And then the Hexagon SDK, that is the tool chain for that DSP. So it's a whole different instruction set architecture. It's got its own set of tools. So it's a little bit complex to set this all up, so that's why you see the Docker here. The idea here is that, once you get all this stuff set up, the cross-compile for the ARM64 and for the Hexagon, as long as it's in a Docker, you don't have to worry about configuring your machine. You can just get the Docker going and run the build. Okay, my diagramming and skills aren't probably all that great, but this is kind of a diagram that illustrates a few different concepts and a few reasons why earlier when I was saying it should be easy and it turned out not to be easy. This diagram illustrates a few of those things. Let's see if the laser pointer works here. Let's see. Step off the end. So basically, if we look at, this is the applications processor, and this is down here, the DSP. We need to make these two sides talk with each other. So Qualcomm has, this is part of that proprietary software. It's got this whole mechanism through shared memory, and they call that the Qualcomm Management Interface, or QMI. But that's sort of a proprietary set of code for them. It's intended for people who are developing specific applications for like a smartphone. They'll use all this. Not probably really intended for an open source software package like PX4. So these beautiful green boxes here kind of, there's a sort of an abstraction layer that we had to create to sort of separate that proprietary interface and kind of generate something that we're allowed to share and that we can put into the open source code base. But essentially it's hiding behind it a whole layer of Qualcomm code there to manage this interface that sends messages back and forth between those two processors. If you look actually at the DSP architecture and the way it runs is actually fairly sophisticated, and it's got these kind of different sort of protection domains in it. Similar like Linux, you've got, even in NutX, you can have sort of the protected area and then more of a user area. So they've kind of split it up into three different layers. There's the OS layer, and in fact, when we build this whole image down below, we don't even get the source for that. That's just binary, and there's APIs to use that, but we don't even have source for that. Here's kind of the main layer where PX4 lives. So originally, back when it was first done by Qualcomm many years ago, there was PX4 lived here. And there was a whole set of libraries that allowed it to communicate directly down to access device drivers. Well, one of the first things we noticed as we were trying to get the software up and running on this new chip was that that interface layer between this and the device drivers no longer existed. Qualcomm said, we don't support that anymore. We're not going to give you the source code for it. You're going to have to come up with a different way. So that threw us for a big loop, and that also made the whole effort much more difficult. Ultimately, we had to make it live in this layer here, but there was no way to get it from the PX4 file system directly into here through any of the mechanisms that they publish and have APIs for using the user protection area. And ultimately, we ended up using kind of if you're familiar with sort of dynamically linking shared objects and accessing symbols within that shared object, all those same mechanisms luckily live within this layer of code. And so we were able to create a shared object that we build with that hexagon tool chain, and at runtime, we dynamically load it into this sort of protection domain on the DSP and sort of bind it to these, the green layers there is our abstraction layer of all the Qualcomm proprietary code. And so that'll give us access then directly to device drivers and to this message passing interface back and forth between the application's code. So I think you can see from this is definitely quite a bit different than microcontroller and NUTX. Okay, this slide, basically, there was a lot of challenges in going through this and making this all happen. I've picked out a few of the key areas here. And if you go through the source tree, you'll see some of these as modules and kind of maybe wonder what those things are. So let me go through a few of the highlights here and kind of explain what some of them are. If you see in the modules directory, there's something called MUORB. So as you know, within PX4, everything is based on sending topics, messages around in the UORB. Device drivers can publish sensor information about IMU data or barometer or GPS, and then you have kind of your core modules, EKF, and things that are operating on that, position controllers. And ultimately, you have outputs, actuator controls to control the motors and to make your drone fly. All are topics going over UORB. So that's kind of the basics of PX4. But now we've got this split architecture. So how do you get UORB topics that are flowing around on the applications processor and UORB topics that are going around on the DSP? How do they get back and forth? So that's this module called MUORB. That stands for multiprocessor UORB. And essentially, if you look at the UORB source code, you'll see that there was already an interface defined to allow UORB to be sent over whatever, arbitrary other transport mechanisms called the communicator, and it's kind of an optional thing. And so basically the MUORB is our instantiation, our version of that interface to allow UORBs to communicate with each other. And so the API was already defined as part of PX4 UORB, and this is just our implementation of it. And so this is kind of what abstracts that Qualcomm proprietary code and allows us to, first of all, initialize and send that shared object down into the DSP and get that linked in and set up, and then to start sending advertisements, publish, subscribe, all the standard UART messages back and forth. So that's kind of a very, very core thing we had to get up and running pretty quickly in order for PX4 to be able to do anything. The shell, you probably used to using PX4 shell. Well, now part of PX4 is running down on the DSP. How do you interact with that? Q shell is basically just a remote, a way to access the shell. There is no direct user interface, and so you kind of have to take shell commands and send them down to the DSP for it to run, and then the results come back. That's what that module Q shell is. So another kind of artifact of this split architecture is rethinking things like the shell. Parameters library is still a big open issue because well, if you look at it, it's just a library and it's got all the parameters in there. And now if you've got it living in two places, how do you keep them in sync with each other? So we kind of had to come up with a UART method to be able to keep the two sides in sync. So both sides see the same view of parameters. UART abstraction is a PR that's a work in progress PR right now that'll hopefully be going in soon. But this is another kind of thing. If you look at, this is more of a difference of the OS. So if you look at the CURT operating system running on the DSP, it doesn't have all those POSIX UART kind of commands like how to set the baud rate and all that kind of stuff. And that stuff is copied all over PX4. We have to abstract that out into kind of a PX4 abstraction of UARTs, and then that will allow us to tie it into directly into what the CURT OS supports. Hardware in the loop, that was a whole nother thing. We have a separate interface and a separate driver for that. Allows us to run with the DSP, piping in from Gazebo, the sensor inputs and sending the motor commands back out. Are we doing on time? Okay, so that's kind of some highlights of some of the work. Obviously, if you go visit our booth and you see we have drones and we've actually got this all working, but it's not completely 100% in mainline yet. It's not all upstreamed. If you go get 1.14.0 right now, stable release, it doesn't have all of this in there. It's got some of it in there. We have been upstreaming things, but we're still not completely there yet. So part of the future work is get everything up there. Because right now, in order to build for this platform, you have to go get our fork, pull that, build that. Obviously, we've already got release versions of that, so you can just install Debian files, Debian packages that have all that in there. But if you're going to do your own work on it, you need to pull from our fork. Our target for that is kind of Q1 next year to have that completely upstreamed so that if you go grab 1.14. Whatever it's going to be at that time, 1 or 2, you won't need to go grab our fork anymore. You can just grab it all from upstream. Actually, stepping back, point 1 there. So, one of the really neat things in PX4 is after you have submitted a PR, it runs all these tests. It builds for all these different platforms, and it runs a bunch of tests, and it'll tell you, or even formatting, it'll say, you didn't even format your code correctly. It'll spit it back to you and say, you failed some tests. We need to get these builds and tests into that flow so that if a developer's out there and they're developing for their NUTX platform, but it breaks something in this platform, we need to have a CI test that will spit it back and say, oh, you broke this other platform. So that's something we need to work out. But eventually, hopefully, this will be all upstreamed. And then Yes, a mile-long to-do list. There's still tons and tons of things. I have a personal list that's very, very long of many, many things to do. So we do a lot of that at ModalAI. Shout out to Ascend Engineering. They're one of our key partners. They've been helping us out a lot and doing a lot of PX4 work for us as well. And obviously, it's open source, so we welcome any kind of contributions. If you're developing on one of our platforms and you have something that you think needs to be changed or updated or even a bug fix, which is great, generate a PR into our fork and we'll pull it in. We'd be happy to have you contribute as well. So yeah, I think thank you, and open it up for some questions. Eric?
Are there any tools available to profile the DSP to get a little bit more insight of how much resource utilization is happening?
Yeah, great question. So tools to profile DSP, resource utilization. So there's a number of different things. In the SDK, there's actually a profiling tool that will do kind of thread level profiling, and we have that enabled within the kernel that's running there. So there is a way to do that. It's not, I wouldn't call it straightforward. It's a little bit challenging to get that going. But at a much higher level, just a raw CPU utilization, like as it's running, how loaded is the DSP. So I need to that's one of the mile-long to-do list things is there is something that we have that we use that's kind of based on some of the Qualcomm proprietary stuff that needs to be brought into PX4 so that, PX4 obviously has CPU monitor topics and fail safes that look at that and all kinds of stuff. It's not currently integrated into that. So that's step number one, is just get the basic CPU load, because that can be really important. Obviously, in a real-time system, if it's getting overloaded, bad things can happen. So, but then, yeah, beyond that, there is sort of profiling tools available. At the end of the day, probably, if you saw the keynote about logging, it's really logging, and printf is ultimately still a lot of the main debugging methods. There is a decent, because of the way the operating system is handled, if something bad does happen in PX4, you access a null pointer or something like that, there is an exception system that will trap that and send a report up to the application side and say, hey, the DSP just suffered a fatal exception. It gives you some information about it, and then it goes and resets the DSP. But yeah, it's a little challenging for sure. It's deeply embedded in the device, and so getting access to it and getting debug information can be challenging. But over the couple of years we've been working with it, we've been able to figure out ways to get all that out. Between 50 and 60. Okay. It's actually, in fact, Ascend was just helping us with some of this, kind of characterizing some of the different loads. It's actually around that level when it's running all its fail safes and pre-arm checks and all this stuff, and then after it takes off, it actually, in flight, is actually lower. So it's actually more around 40% while it's actually flying around. It's more when it's on the ground that it tends to be running more checks and taking up more CPU.
And then, is there bandwidth constraints going between the DSP and the application processor?
There is. Eventually, there's ways to, but I mean, it's just two processors and a shared memory interface. So I mean, it's pretty high bandwidth. Yeah, it's. Well, nothing, it's gone. Like, I mean, like, you just kill it, it's gone. So obviously you lose your connection, your network connection, so if you're connected to the ground control station, that goes away. You don't see that anymore. And it depends on how you're controlling the drone. Obviously, if you're controlling it through the network link, you've lost that, then it's going to drop into some sort of a fail-safe, and whatever you've got your fail-safe set to land or whatever. If you're just flying with sticks, though, the sticks, they go directly into the DSP. That's kind of part of the real-time flight control. And so, you know, like if I'm doing these tests in hardware in the loop so that, you know, if I crash if I kill the apps processor side, and I'm using a real drone, something horrible could happen. I typically do this kind of stuff in hardware in the loop testing. Yeah, you can keep flying it around with the sticks and land it or whatever. But typically, I think you'd probably want to fail safe to say land it for you or something. But it's still going, so you have that ability. Other questions? James. No. But we can produce one. I can tell you off the top of my head, Logger, Data Manager, Navigator, Mavlink. Those are the ones running on the applications processor in all our configurations. Otherwise, everything else is on the DSP. Yep.
How easy to switch from one to the other?
It's basically you're building two separate things. You're building the DSP and you're building the application side. So it's literally just, you know, the default .px4 board file that's got all the configs that you set to yes to include that module, just include it on the other side. And in fact, in some cases where some of our earlier architectures had, like maybe GPS could be on the application side or maybe it could be on the DSP side. It's built into both and it's just in the start script which one gets started. Do you start it on? So it's literally all there. It's just whatever gets started at runtime. Yeah. To run the entire PX4 flight stack on DSP, including, I mean, we are actively trying to get more and more modules over, but there's really two aspects of it, I think, that make it a little bit more challenging for the final modules that we still have over there. For example, the logger has got direct access to the file system. The DSP has sort of a more indirect access to the file system. So if you were to put the logger on the DSP side, we need to characterize kind of what is its true bandwidth to be able to write log items into the log file and store those and make sure that that we can do that. And so that's why that's still on the application side. Obviously Mavlink is heavily dependent on the networking stack and opening sockets and all that kind of stuff. And so in order to move that over, we need to kind of create an abstraction for its communication method instead of using networking stack or serial port directly, but to use this sort of QMI shared memory. So, you know, theoretically, I think there's a route forward if you wanted to run it all on DSP, but because of the file system mainly and the networking stack, it's just those modules are the last ones on the application side. Another question? Yep. The Navigator? Navigator has a lot of dependencies on Data Manager and directly, yeah, so it's kind of tied in directly to some of that stuff. So some of it's not, it itself maybe doesn't, but it's got these dependencies that yeah. Other questions? Okay, thank you very much.